Hello yet again, and welcome to another review session for your final exam in Calculus 3208. We're still in the unit on anti-differentiation and integration here, and this is our fourth session. And today we're talking about applying what we know about initial value problems and integration to solve problems involving rectilinear motion. And according to your curriculum guide, this is the only application topic you have to do for these particular type of questions. So let's make sure we nail this one down pretty good. All right. Here we go. A couple things we have to talk about. We're used to looking at rectilinear motion problems already in the course, but we always start with position and work our way forward to velocity and then to acceleration by using derivatives. Well, we're going to go the other way this time, from acceleration back to position. And we're going to solve rectilinear motion problems with given velocities or accelerations. We can start from either one of those places and find information about the position. So let's see what's going on now. Let's remember that we had relationships between position, velocity, and acceleration as defined by derivatives. So if s of t was our position function, v of t was the derivative of that, the rate of change of position with respect to time, and that's what we called our velocity. And if a of t is the acceleration function, we said that was the derivative of the speed function, or the velocity function, I should say, which is the second derivative of the position function. So that's our acceleration. And those are the relationships that we use to go from position through to acceleration. But we can go the other way now because we know about integration and antiderivatives, right? So if we start with acceleration, we could say that the velocity function is going to be the antiderivative of the acceleration function, going backwards, or the indefinite integral, I should say. And if we want to look at displacement or position, that would be the antiderivative of the velocity function. Okay, so that's how we work backwards through these things. And let's just jump right into some examples and see how we put that stuff into action with initial value problems. Okay, so what we have to do now is we're going to have to look at a particle is moving along an x-axis. So that's the typical situation that we get with these. And its velocity is given by an equation. If the particle is 5 units left at of the origin at time t equals 0, where is it after 10 seconds? So there's some extra information given here. This is the question. We want to know where is it after 10 seconds. So our ultimate goal here is defined. What is s of 10? That's what we're after. Everything else they tell us here, we're 5 units left of the origin at time t equals 0. That's our initial condition. So what they're saying there is that s of 0 at time 0, 5 units left of the origin will be -5 for our position. Okay? So let's go and get our position function so we can evaluate where this guy is. So v of t they told us was this, so that means that s of t will be the antiderivative of that. So s of t is going to be 3t cubed over 3, which is just t cubed, minus 4.9t squared over 2, plus t, and an arbitrary constant c. So we'll use our initial condition now. So s of 0 is -5, so when t equals 0, we've got this stuff shaken down. And these three terms are all going to disappear because they're all 0 anyway, so it tells us our value for c is -5 based on our initial condition. So that tells me two things. Number one, my position function is s of t equals t cubed minus 4 9/10 over 2 t squared plus t, and plus my constant, which is now, minus 5. And it tells me that I can now solve my problem. So I solve this by finding s of 10. So s of 10 is going to be what I get when I plug 10 in there. So I've got 10 cubed minus 4.9 over 2 times 10 squared plus 10, and then minus 5. So let's see, 10 cubed is 1,000. 4.9 times 10 squared. So 10 squared is 100, so that's 490. And 490 divided by 2 is going to be minus 245. And then 10 minus 5 is 5. So we can put all this stuff together. Let's see what we've got now. 1,000 minus 245 is 755, plus 5 is going to be 760. So we got 760, and that is where we are, so we're going to be units, and that's going to be to the right of the origin. Alrighty, good stuff. So let's go on and try another one now. Okay, so in this question, a particle moves along an x-axis so that its velocity is given by this function. So we have velocity again. What's its change in displacement between times t equals 1 second and t equals 3 seconds? And in which direction has it moved? Okay, so we're not looking for a specific displacement, just a change in displacement. And you'll notice that there's no initial condition here. They just ask us a question about how it's changed between time 1 and time 3. And you'll see in a minute how that is going to be okay. We're going to be able to get away without using an initial condition because of that. So let's see how this fits together now. So the velocity function they gave us was 12t minus 5, for positive t. So then our position function, s of t, oops, forgot my t, is going to be, let's see, 12t squared over 2 is 6t squared minus 5t plus an arbitrary constant, which we don't know and have no way to figure out. But as it turns out, we won't care, because we want to find the difference in our position, the change in position, where do we start and where do we end up? So that's our change in displacement between these two times. So we're actually looking at finding s of 3 minus s of 1. So let's see what that is. S of 3 is going to be 6 times 3 squared minus 5 times 3 plus an arbitrary constant c. So this is our change in position or displacement here. Okay, so we've got that part, and then we have to subtract s of 1, which is 6 times 1 squared minus 5 times 1 plus our arbitrary constant c. And since we integrate it once and got the same constant and we're filling into the same formula, we have a c here minus a c there. We don't need those. So we just need to work out the rest of it. So 6 times 3 squared is 69. So it's 54 minus 15. And then we have to change the sign of everything inside on this side. So it's going to be minus 6 plus 5. So if we put all that together, we're going to have 54 minus 15 minus 6 plus 5. So 54 minus 15 is 39. And then the net effect over here is subtract another 1. So we get positive 38. And it didn't give us units, so we'll just say in units. So that's our net change in displacement. And in which direction has it moved? Well, if this is an x-axis and we've gone to this position, this is our change in position. So that's to the right, or in the positive direction, if you will. Alrighty, so let's take a look at another question now. A particle is moving along the x-axis so that its acceleration is given by this function. I almost wonder if we shouldn't have brackets there to say all of that in meters per second squared. How fast is the particle moving after 5 seconds if its initial velocity is this? So this time we're starting with an acceleration function, and we want to find out its speed after a certain time, given an initial condition for velocity. Okay, so the initial condition, they tell us, is that we start off moving at -7 meters per second. And then from our acceleration function over here, we just anti-differentiate. So acceleration was 5t minus 2, which means that our velocity function, v of t, is going to be 5t squared on 2 minus 2t plus an arbitrary constant, c. All right, so v of 0 equals -7. We have -7 equals 5/2 of 0 squared minus 2 times 0 plus c. So the arbitrary constant then is -7. So that means we have our position function. V of t is 5t squared on 2 minus 2t minus 7. So what we have to figure out now is where are we after, or how fast are we moving after 5 seconds? So we want v of 5. It doesn't say which direction, so it doesn't matter if it's positive or negative, I guess. 5/2 of 5 squared minus 2 by 5 minus 7. So let's see, that's 125 over 2 minus 17. 125 over 2 is 62.5. So 62.5 minus 17 will be 45.5. My arithmetic serves me okay. So 45.5, and that's going to be in meters per second, and we're moving to the right here. Okay? They didn't ask, but we told them anyway. Let's see if we can get one more example under our belts for this stuff before we get into some things for you to do. Okay. A particle is moving along the x-axis so that its acceleration is given by this much. Determine the particle's position after 2 seconds. If at time 0, it's 5 meters left of the origin and it's moving at 3 meters per second. All right, so here's what's going on. They tell us our acceleration function, and it's a very simple one. A of t is a constant, -7. Then what they tell us is that initially, at time 0, we're 5 meters left of the origin, which says that s of 0 is -5. And we're also told here that at that time we're moving at 3 meters per second, so our v of 0 is moving to the right a +3. So based on those three things, acceleration being constant, we have to determine the particle's position after 2 seconds. So we need a position function. We're going to have to take 2 antiderivatives to get there, and we're going to have to use 2 initial conditions to get rid of those arbitrary constants. Okay, so v of t then will be equal to -7t, whoops, there's the negative, plus some constant c. So I'm going to use my initial condition I have for velocity to get rid of this c. So I say that 3 equals -7 by 0 plus c. So then c is just equal to 3. Okay, so that tells me then that my velocity function, v of t, would be equal to -7t plus 3. Okay, so we've got that bit worked out. So the next thing we have to do now is we have to work out what is going to be our acceleration, or sorry, position function, s. So s of t is going to be the antiderivative of this. So that's -7t squared on 2 plus 3t plus another arbitrary constant, we'll call it d for this one. Okay, so they tell us that s of 0 is -5, so that means -5 has to be equal to -7 times 0 squared over 2 plus 3 by 0 plus the last arbitrary constant we had, which was d. So -5 is going to be the value of d that we're after. So now we have our position function finally, and we're able to evaluate it to find out what we're after here. So s of t is -7/2 of t squared plus 3 by t minus 5. So we have a quadratic position function, and we need to find its value after 2 seconds. So s of 2 is what we need, and that's going to be -7 over 2 times 2 squared plus 3 times 2 minus 5. Okay, so s of 2 is going to be equal to, let's kill one of those with this one. So it's -14 plus 6 minus 5. So that's -19 plus 6 is -13. So that's going to be according to this in meters. So they're asking us, what is the particle's position after 2 seconds? So after 2 seconds, we are 13 meters left of the origin. Okay? So that's where we are, 13 meters left of the origin. All right. So next is the or turn question, and it's similar to the one we just did, just some different numbers given. A little bit trickier though, because acceleration doesn't start off as a constant, it starts off as a linear. But that's okay, the actual algebra involved is not too bad. So you should have not too much trouble with that, I hope. I'm going to flip to the solution now, so if you'd like to pause the video, please do so. So here's the solution to the or turn question. The particle moves along, blah, 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 blah. You can work it all out. In any event, I hope you're getting the right answer for these things. We're using lots of antiderivatives here. And from there, we'll jump on and do a quick summary of all the stuff that we talked about in this session. So in this session, we have looked at rectilinear motion problems using indefinite integrals when the given information is about velocity and we need to know position. So when we had that, all we had to do was just one integral. Okay? If the given information is about acceleration and we need to know about velocity, that's also just one integral. But if it's about acceleration and we need to know position, that means we had to integrate twice. So that was about two integrals. Okay? The relationships between acceleration, velocity, and position are described by some integral equations. So not differential equations here, integral equations, which look like this. And we saw that was the acceleration function is where you start from, and its antiderivative will be your velocity function, and then its antiderivative will be your position function. And when sufficient initial conditions are given, we can determine each of the equations as a particular antiderivative. So that's right, that's what we did. Well, I hope that that was helpful and that you learned a few things here and that your studying is going well in general. And if you have any questions, please don't hesitate to post them up on D2L, and I'll do my best to answer them. And we'll get you ready for that exam by hook or by crook. We hope you're going to be ready. All right.